Welcome back to the Foundry by Forge College. I am absolutely thrilled you're hanging out with me today. So, in our last explainer, we took this big, wide-angle look at the landscape of energy consumption and mining. We talked about seasonal variations, geographic differences, and really just the broad strokes of how mining interacts with the power grid. But today we are taking off our observer hats and putting on our hard hats. We're transitioning from just understanding that landscape to actually calculating and modeling it exactly like an engineer would. We're going to build some concrete, mathematical models together, which will let you confidently estimate energy use across entirely different setups. It's going to be a lot of fun.
Here's a quick look at our blueprint for today's explainer. First up, the mining energy toolkit. Second, the core energy equation. Third, 3 real-world scenarios. Fourth, building a comparison table. And finally, sensitivity and final checks.
All right, let's dive into Section 1, the Mining Energy Toolkit. Time to gather the basics.
Let's kick things off with PUE, which stands for Power Usage Effectiveness. You can basically think of PUE as the inevitable overhead tax of running any mining facility, because, well, a miner doesn't just run on magic, right? It generates heat. A lot of it. So PUE accounts for the total power used by the whole facility. That means the lights, the networking gear, and crucially, those massive AC and ventilation units that keep the miners from literally melting themselves. To put a number on it, if your miners draw 1,000 watts, but your whole facility needs to draw 1,200 watts just to keep them running safely, your PUE is 1.2.
Next up in our toolkit is the duty cycle. This is simply the fraction of time, usually measured on a scale from 0 to 1, that your mining machines are actually hashing away at full load. I mean, if you've ever heard a home miner running, or frankly, even just your laptop fan screaming for its life during a heavy software update, you know that machines rarely run at 100% capacity forever. They need throttling, maintenance, or just a cooling break. So a duty cycle of 0.95 simply means your machines are effectively grinding at full power 95% of the time.
So here they are, the 5 core variables we're going to snap together to form our engineering schematic. We've got hash rate, measured in terahashes per second, efficiency, measured in watts per terahash, the total number of units, our duty cycle, and finally, our PUE multiplier. These 5 puzzle pieces right here, they are literally all you need to accurately predict the energy footprint of almost any mining setup on the planet. Moving right along to Section 2, the core energy equation. Let's build the formula.
Okay, this sequence is your golden rule. Step 1, you multiply the hash rate by the efficiency. That tells you how many watts a single miner uses. Simple enough. Step 2, multiply that number by the total number of machines in your fleet. Step 3, multiply that total by your duty cycle and your PUE. That accounts for real-world downtime and your facility's cooling tax. And finally, Step 4, multiply by the hours in your time period. Say 24 for a daily estimate. Then divide by 1,000. Why divide by 1,000? Well, we need to convert watt-hours into kilowatt-hours, because that is the standard unit you're actually going to see on any electricity bill.
But wait, here is a super crucial distinction for any good model. You have to know the difference between nameplate efficiency and measured efficiency. Nameplate efficiency is just what the manufacturer prints on the side of the box. Measured efficiency is what actually happens when you plug the thing in under real-world hashing and cooling conditions. As you'll probably explore if you take some of our more advanced engineering courses at Forge College, theory and practice can be wildly different. Manufacturers love ideal, perfectly controlled steady-state lab conditions. But smart engineers, they always use an efficiency adjustment factor. They might bump up that nameplate rating by maybe 5% to reflect the messy reality of fluctuating room temperatures and weird firmware quirks. Let's jump into Section 3, 3 real-world scenarios. It is time to test these prototypes. This setup brilliantly illustrates the vast differences in how people actually deploy these machines. Think about a home setup. It might be just one tiny unit with a fractional hash rate and a super low duty cycle, probably because it gets way too hot in the closet and has to be turned off. Now contrast that with a co-location facility at the complete opposite extreme. We're talking 100 high-powered units running at 110 terahashes each. They've got a slightly better efficiency of 29 watts per terahash and an incredibly optimized duty cycle of 0.99. That industrial setup is heavily utilized and highly efficient. So when we run that co-location scenario through our 4-step equation for a 24-hour period, we get this number: 8,334 kilowatt hours consumed in a single day. Just let the scale of that math sink in for a second. A typical American household uses about, 30 kilowatt hours a day? This 100-unit facility is pulling down over 8,000.
And this right here is exactly why we rely on models, not guesses, because the numbers scale up incredibly fast.
Section 4. Building a comparison table. Let's start actually constructing the model.
Setting up your spreadsheet requires a bit of discipline. First, you want to define really clear labels. Use things like home-1 or colo-100 and set your scope. Are you looking at daily, monthly, or annual use? Make that clear. Second, gather and normalize your parameters. I literally cannot stress this enough. Keep your units consistent so the math doesn't break down later. Always convert everything to watts initially. Third, compute your device level power, and then just multiply by your unit count to get your raw fleet power in watts.
Moving right along to the final steps of our table. Step 4 is where you apply your duty cycle and your PUE to get the adjusted facility power. Then, Step 5 converts that into your final energy output in kilowatt hours. Now, I want you to notice how we separated the device-level parameters, like hash rate, from the site-level parameters, like PUE. This modular approach, it's the absolute secret sauce of a great spreadsheet. It allows you to easily swap hardware in your model without having to rebuild the whole facility's environmental assumptions. And finally, Step 6. Add sensitivity columns. You want to test how a 10% shift in efficiency completely changes your bottom line.
And finally, Section 5, Sensitivity and Final Checks, Validating the Data.
Look, you should always run these basic sanity checks before finalizing your table. Did you verify your unit conversions? As a general rule of thumb, if your math says a single home miner sitting in a garage is using the equivalent energy of a small city, yeah, you probably just forgot to divide by 1,000 when converting watts to kilowatts. We've all been there. Also, make sure your PUE actually aligns with the facility type. And most importantly, document all your assumptions in adjacent cells so someone else can actually reproduce your work.
To sum up the whole methodology for you, keeping your units strictly consistent, cleanly separating what the device does from what the site does, and relentlessly documenting your assumptions. Those are the 3 pillars of creating a defensible model. Honestly, a spreadsheet full of numbers is pretty much useless if you can't explain exactly where they came from. And that brings us to a bit of a cliffhanger. Thanks to the toolkit we've built today, we can now calculate the exact energy used by virtually any mining setup out there. But it leaves us with a massive, looming question. Where does all that energy actually come from? Is it coal? Is it hydro? Is it stranded natural gas? Well, that is exactly what we are going to tackle in our next module on renewable integration and geographic considerations. If you want to dive deeper into that and explore plenty of other fascinating Web3 topics, I highly encourage you to visit forge.college to continue your learning journey. Keep modeling, stay curious, and I will see you in the next explainer.